This is a video project for fields and applications. The question we will be answering is find all irreducible polynomials of degree 4 in the set of polynomials over F3. Before we begin solving the question, I'm going to write down 4 observations that will make the question easier to solve. So, observation 1. Function g of x is irreducible if and only if g of x times a constant is irreducible. And the constant is in F3. Note 2, polynomials of degree 4 are either irreducible polynomials of degree 4, or they are products of irreducible polynomials of degree 3 times a degree 1, or they can be a degree 2 times a 2, or a 2 times a 1 times a 1, or a 1 times a 1 times a 1 times a 1, where all of these represent irreducible polynomials. Just to finish off that note, we can check to see if the degree 1 irreducibles are factors of the degree 4 polynomial, and if they are, we can rule those out, which means we just have to check the degree 2 by 2s. Note 3, if we consider a polynomial of degree 4 as an a0 plus an a1x a2x squared plus a3x cubed plus an a4x to the 4, and we let a0 equal 0, then clearly x is a factor. So that polynomial will not be irreducible. Note 4, just counting up the number of polynomials we need to check. There is one option for the value of a4. There are 3 for a3, 3 for a2, 3 for a1, and then we're just not letting a0 be 0. So that gives 2 options, which is 54 polynomials to check.
To make our life easier, when we're given a polynomial, we're going to rewrite it in a shorter form. So a4, a3, a2, a1, a0. For example, if we're given a polynomial, x to the 4 plus 2x squared plus 1, we're instead going to rewrite it as 1, 0, 2, 0, 1.
If our given polynomial, p of x, has a factor of degree 1, let's say x minus a, then when we evaluate it at a, we will get 0. So what we can do is we can look through all of our polynomials and evaluate them at x equals 1 and x equals 2. And then if we get 0, we can cross them out. So if we evaluate p at 1, we get the following. a4 plus a3 plus a2 plus a1 plus a0. So really what we're doing is we're just adding up all of the numbers in our covert. Plugging in x equals 2, we'll get the following. 2 is equal to minus 1. 2 squared is equal to 1. 2 cubed is equal to minus 1. And 2 to the 4 is equal to 1 again. So what we're doing here is we're taking a4 minus a3 plus a2 minus a1 plus a0, the alternating sum. As you'll see here in the following examples, but you don't get to see them yet.
Now that we've found all the polynomials with a linear factor, we need to find the polynomials with quadratic factors. So we're going to use the same procedure as before, but just this time, instead of finding the linear factors, we'll find the quadratic factors. Now that we've found the irreducible quadratic polynomials, we need to multiply them together in pairs, and this will result in some degree 4 polynomials that we need to remove from the list of potential irreducibles.
This is a set of all monic irreducible polynomials of degree 4 in the set of polynomials on F3. However, because of note 1, we can only include these polynomials, and they will only be irreducible if lambda times t is also true. So we've multiplied all of these polynomials by 2 to give us 18 more polynomials. So this, altogether, is a set